Okay. Today we will do several things that will lead to the Smale name of a person, Horseshoe Map. And this is really important for understanding chaos. Okay, and it involves a different kind of thinking with symbols, and you will see how that works. But to do that, we have to do a few things first. So first, think of the Cantor set that we have studied already. The Cantor set is constructed like this. We start with an interval, but then we remove the middle third of the interval. And then from each of these two remaining intervals, we remove the middle third. And then from each of these remaining intervals, we remove the middle third. And from each of those remaining intervals, we remove the middle third. And so on. And in this way, we go to infinity. We have considered the box counting dimension of this set, but today I will do something else. Okay. So what I will do now is I will say consider a point x that is in this set. Now it is either in this half or in this half. So let's call this 0 and call this 1. And so I will put a digit here, d1. It's a binary digit. It is either 0 or 1. And if it is 0, I know that it is on this side. And if it is 1, then I know it is on this side. Okay. Now at the next level, it is either here or here, which I will again label with a 0 or 1. And then over here also it could be either here or here. So it's 0 or 1. And so my next binary digit is d2, which will tell me whether it is on the left side or the right side. And then over here there is a 0 and a 1 and so on. And in this way, a point on the Cantor set can be labeled like this. What is interesting is that when I give it a finite number, any finite number of these digits, I still have an interval of strictly non-zero length. So there are infinitely many, uncountably infinitely many points which have the same number of digits. The same digits for any number of digits. Okay, so there is one issue there. You can think of every point in the set being labeled in this way by a binary sequence. So 0 1 1 0 0 0 1 1 0 0 0 0 1 1 and so on, and then 1 0 0 1 0 0 0 1 1 0 0 and so on. And then there are these arguments that people use when they are trying to decide whether sets are countable or uncountable, and from that you know that this set is uncountable. And I am not going to go into that, but I will show you that my intention here is for you to see that points in the Cantor set can be labeled like this with a binary sequence. Okay, so you move forward. As you let us say specify several digits, you get into a little interval and you know the point is somewhere in that interval, and you specify more digits and you get an even smaller interval and so on. In this way you get very, very, very close to the point as you specify a large number of such digits. So this is about using this kind of binary digital coordinate system for describing points in the Cantor set. That is the first observation. Now let me show you a map. So this is a simple map. And the map is like this. Xk plus 1 is equal to 2xk mod 1. What this means is, if this is for x in, well, we can go with 0, 1, it doesn't matter. We'll include 0. Okay, it doesn't matter. Now, what this means is if 2xk is more than 1, you subtract 1. Okay, so let me give you an example. suppose x is 0.3, then it goes to 0.6. Twice that is 1.2, that becomes 0.2. Twice that is 0.4. Twice that is 0.8. Twice that is 1.6, which is again 0.6. Interestingly, you've settled on a periodic orbit. Okay, so you started from here and it's a periodic orbit now, 0.6 to 0.2 to 0.4 to 0.8 and then back to 0.6. So this is a period 4. Obviously, most things are not periodic. So for example, you could start with 1 over pi, for example, and then it will just be an aperiodic sequence. Okay, so this is something to note. What is interesting is that x being any fraction between 0 and 1 can be represented as d1 by 2 to the 1 plus d2 by 2 to the 2 plus d3 by 2 to the 3 plus d4 by 2 to the 4 and so on. And in this way, if I describe x like this, then I can basically call it as equivalent to this sequence of digits, and each of these d's is also, each d is 0 or 1. Okay, so what happens here is this is a binary sequence. In the decimal expansion, we have d1 by 10 to the 1 plus d2 by 10 to the 2 and so on, and these digits are allowed to be anything from 0 to 9. Over here, this is, you can say, a binal system, so or a binary system. In place of the decimal point, we have a binal point, if you like. It's just a name to match decimal. Okay, it's just a name. So now this here, this sequence represents x. If you can represent x using the decimal system, you can represent it using the binal system. There is no problem. And then what happens now is that each time when you double it, what happens is this point just moves to the right, and if this number happens to be 1, you drop it, and if it is 0, nothing has changed. Okay, so this was 0 already, and so this dynamics corresponds to shifting by 1 and dropping the left side. Okay, so drop 1 digit, move everything left. Okay, when you think about this dynamics in this way, something interesting happens. You get some significant understanding. So let me point out what that is. Oh, I should probably, let's see now. Let me follow here. Apologies. Okay, here. So let's say 0 point, d1, d2, d3, d4, d5, d6 and all the way. Now what happens is, suppose 100 digits match and then different. So I have two x's. Okay, so what is the difference in their coordinates? The difference in their coordinates is basically, 2 to the power minus 100, right? That is the difference, or 101, whatever. Okay, but what happens is, after approximately 100 steps, they have nothing to do with each other. They are completely different sequences. You are familiar with this, right? So the very, very tiny difference between them grows exponentially, grows by a factor of 2 with each iteration of the map, until the distance between them becomes comparable to 1, which is the size of the final set. However, it's not an attracting set. Points keep leaving the set, right? So this is a map where points keep leaving the set only x equals 0 stays forever. Okay, so now we will come to the horseshoe map, and we will see that the horseshoe map has this kind of a binary digit expansion, except there is a complication. It is a double infinite series, but it is two infinite series of binary digits. It has exponential separation of nearby trajectories. It also is not an attractor, which was important for chaos, but over here we are dropping that for understanding. It has infinitely many different types of infinitely many different periods of periodic orbits. It has exponential separation of nearby trajectories. It has other things. I mean, there is actually an invariant set that is uncountably big instead of just one point, and those points, the map becomes invertible and so on. So that is what we are going to see in the horseshoe map, and that is why the horseshoe map is so famous. Okay, so here we are now. Now we come to the horseshoe map. And the horseshoe map, you can think about it first like this. So you take a square, and what you do is you stretch the square so that it is tall and narrow, and then you bend it like this, and you put it back on the original square, and so, you know, like here, and you retain the parts that are inside the square and discard the parts that are outside. Okay, so now let me point out, here is the square. It became long. You kept only these parts, you discarded the rest, and so this is what remained. Now, of course, there is a little margin over here which we will remove for simpler thinking. These points are lost. Okay, now over here, this is an interesting point. Here nothing is mapped here. Well, nothing is mapped here either, but we will get rid of that margin. Okay, so this is the horseshoe map, and there are rather remarkable things you can understand about chaotic dynamics when you think about the horseshoe map. Okay, so we are going to think about it now, and the way we will do it is we will first get rid of that margin, and so after mapping, what we will get is two strips, one here, one here. This one I will mark as green, this one I will mark as blue, this one I will remind you nothing is mapped here. Okay, now when you look at this part, you will realize that this bottom part is the part that got mapped here. Okay, so this is the part that was green, you see. This is the one that went there, and this is the blue part. Let me draw a boundary here. This is the blue part. So this blue part went there, this green part went there, these lost. We don't care about them, we never saw them again, and nothing got mapped here. Okay, so this is really the essence of the horseshoe map. Okay, there is something that you have to understand, and it's really important, and that is that every point inside this rectangle has an inverse, right? This point does not have an inverse, no inverse, because nothing got mapped here. Points from here got lost, they did not get mapped there, but every point over here got mapped to something here, and every point here has an inverse. Okay, so some part of it is invertible. Similarly, every point here got mapped to something here, and every point here has an inverse. Okay, so this is for one evaluation of the map. What about 2? Okay, so when we think about 2, it gets more interesting. Why is that? That is because if you are in this region, you don't get mapped. So we have to come here, and what we have to do is we have to, well, we'll use the eraser. We will erase this part and say if you are here, then in the next mapping you're out of the square. And so really we are concerned with this part. This is the part that will survive 2 mappings. But now when I look at the pre-image, what that means is that this is the part that will survive 2 mappings. Similarly over here, because of the stretching, this is the part that will survive 2 mappings. Okay, but now it is invertible. Okay, how about 3 mappings? Right? So when this one is mapped, when this one is mapped forward, right? So what will happen is that this lower part with the blue here and the green here, right? So let me put here a blue and a green just as a label. Both of this will be stretched to full length, this will be stretched to full length, it will be squeezed like this, and so what I will get is I will get the green part and the blue part that came from here, from the lower part, and this part will be inverted, and so the blue part will be here and the green part will be here. This is how it will be mapped. Okay, all right. And so this let me use red now and point out, if I call this one A, that is A prime, that is where it gets mapped. If I call this one B, that is B prime, that is where it gets mapped. Okay, then if I call this one C, then that is C prime, that is where it gets mapped. If I call this one D, then that is D prime, that is where it gets mapped. Okay, and now if you think about points that are there in the pre-images as well as in the mapped images, then we have to take the intersection of this one, and so then we get and so on. And I hope you can see what is happening here. If we go forward infinitely many times and we go backwards also infinitely many times, because we are only looking at that portion of the square where it has inverses, and we are insisting on finding those sets which have those points which can be inverted infinitely many times and mapped forward infinitely many times and then never leave the square. That is a very special invariant set. So that invariant set that invariant set which allows infinitely many forward or backward iterations. That invariant set is a Cantor-like set, right? It's like a two-dimensional version of the Cantor set. So that's interesting. It has uncountably many points. Okay, you can calculate its box counting dimension if you like. Okay, but we are interested in something else that is even more interesting. Because forward and backward iterates are both allowed, now we can just look at this part here. So what we can do is we can look at these two horizontal stripes, and we will call this one H0 and we will call this one H1, and we can describe any point in the invariant set, like this. So we will say there will be a binal point, and then we will have D1, D2, D3, D4 like this, and D minus 1, D minus 2, D minus 3, D minus 4 like this. So this is our characterization of points in the invariant set of the horseshoe map. Okay, and why is this important? How is this defined? This is defined like this, that a point X, right, is defined using these D's such that if I forward mappings lead the point into H0, then di equals 0, and if something leads into H1, then di equals 1. Okay, now this is very remarkable. When you look at the pictures that people draw, it is actually hard to understand it, and you have to pay attention to understand the geometry. But if you look back at what we have said, we are looking at an invariant set. Infinitely many mappings are possible. Each time it is mapped, it has to be in one of those, and that is how we define these points. In that case, you see now when you look at these dynamics, the dynamics correspond, the forward dynamics corresponds to this point hopping, this digit moving like this, right? So d minus 1 is a minus 1 number of forward maps, that is one backward map, one pre-image. Okay, and then you see something very, very interesting can happen now. What can happen is that, first of all, if a very large number of digits are common, same, and then not same, right? So then you have exponential separation of nearby trajectories, right? Because with each mapping, the distance is halved in some metric, and then beyond a point, they have nothing to do with each other, exactly like the chaotic dynamics we have seen. On the other hand, we could have infinitely many points, or a very large number of points not same, and then same, right? And this means that it is possible for trajectories that are very far away to collapse onto trajectories that are essentially very, very close to each other. Remember that any finite number of these digits leads you to an an interval, or in this case a 2D little square type of place where there are uncountably many points. So basically those trajectories have become very, very close to each other, and then they sort of have very similar dynamics for a very long time. And of course, if your initial condition has uncertainty, then maybe after 40, 400,000, certain number of iterates, then the digits may be different, and once again these trajectories will have nothing to do with each other, right? You can take 75 of them, any binary sequence, and then repeat 75, 75, that will give you a periodic orbit. You can have 2 to the power 75 possibilities for 75 digit long binary numbers, and so that is the total number of types of periodic orbits you can have of periodicity 75 mappings and so on. In this way you can see that it is an invariant set. The only thing is that it is not an attractor, but this invariant set has very complicated dynamics. It has an uncountably large number of points. It has a very large number of points of periodic orbits. It has a very complex orbit that sort of gets close to any point, any number of points that you want. There is exponential divergence of nearby trajectories. There are trajectories that can be very far apart for a very long time and then get very close to each other. Okay, so in terms of the possibilities that we have seen in chaotic dynamics, this map, the horseshoe map, and this way of looking at it, which is called symbolic dynamics, okay, so this has given us a lot of insight into how this kind of system behaves, and we will look at the consequences or applications of this later for the Duffing oscillator.